Welcome to week 9, and this is going to be part A of this last week of actual new work, and this will be our last actual Edpuzzle lesson for the year. Yay! This might be a little bit longer video. I'm going to do a lesson on conservation of energy to analyze the motion of objects, and then I'm going to talk a little bit about your final assignment, the lab, that I will post this week also. So the end of this video will be a little bit about the lab that you'll be doing for your final grade. So today's objectives, you're going to learn how to use conservation of energy to analyze the motion of objects. If you guys remember, total energy is going to be the potential energy plus the kinetic energy. So you add these energies together. They're all joules. Potential energy is from the height, and kinetic energy is from the speed. So you add the mgh and the 1/2 mv squared together, and you get the total energy of the object. That's going to be conserved. What does that mean, conserved? Total energy is conserved. It means it stays constant for a system or an object, as long as there's no energy loss due to friction or heat. And when we say loss, it just means it leaves the object, but it goes somewhere else. Overall, we're going to be adding potential and kinetic energy together and seeing how it stays the same during a motion. So let's just spend most of the time just talking about one main example. Here we have a kid on a sled on the ice, on snow, and how much total energy does this kid on the sled have on the snow at the top of the hill? And they're starting at rest. They're going to start rest and barely move forward and let gravity pull them down the hill. So they're starting at rest at the top of the hill. The kid in the sled's mass is 30 kilograms, and then we'll say the hill is 6 meters tall. And the question is, what's the total energy the kid has up there? So you remember, total energy is potential plus kinetic, so we just got to take the potential, mgh, mass times little g times height, and add to it the kinetic energy, 1/2 mv squared. We add these together, and that should be the total energy of the kid in sled. We'll set this up like this. Here's our givens, and here's potential energy equation. We can plug them in and solve, and we have kinetic energy equation. Plug them in and solve. We'll go through this and look at our situation, and we'll go through the givens. So what goes right here in front of the M? This is the mass, is 30 kilograms. What goes in front of the V? I'll give you a hint. It's a kid at the top of the hill. So what's the velocity at the top of the hill? He's at rest, so it's going to be 0. And then finally, H. Well, we plug in for the H. That's the height, is 6 meters. 6 meters. So those are our givens, and we're solving for. That's the G, the U, the unknowns, potential energy, and kinetic energy. And then the E, GUE equation. Here's our two equations, mgh and 1/2 mv squared. So we're going to plug into mgh. And what's our first number of mgh? 30. 30 goes there. What's our second number of mgh? G is 9.8. And the final number in the equation, mgh, height is 6 meters. So we plug in our calculator, 30 times 9.8 times 6, and we end up with 1,764 joules of potential from the height. And that's work that the kid probably had to do with his legs to walk himself up the hill and get ready to slide down. Now the kinetic energy, 1/2 mv squared. So the 1/2 is 0.5. The M I already did for you. It's 30, 1/2 times the M, and then what goes right here? It's V squared, so it's going to be, wait, 0. 0 times 0, so the kinetic energy is going to be 0. That makes sense. Kid's not moving at the top of the hill. He's just sitting there getting ready to slide down, so no kinetic energy. It's all potential energy. So the total energy is going to be something plus, the kinetic is 0. That goes there. So what is the total energy of the kid on the sled at the top of the hill? It's just the 1764, the potential energy, plus 0. So 1764, that's the total energy. The total energy is it's all potential. At the top of the hill is all potential energy. Okay? And so now he's going to slide down the hill and pick up speed. We're going to turn potential energy into kinetic energy. So the second part of this problem is going to be, How much kinetic energy does the kid on a sled have at the bottom of the hill? How much kinetic energy do you have? All right, so we have our equation, 1/2 mv squared. So we plug in our givens. What we put in here for the mass? We're going to put in the mass of the kid, which was 30 kilograms. 30 kilograms, okay? And then the velocity, plug in the velocity at the bottom of the hill. And that's going to be, well, this is at rest, but that's at the top of the hill. How fast is it on the bottom? Wait, we don't know. We don't know. We have no idea. We don't know the velocity, so we can't plug in the velocity. We can't how do we calculate the kinetic energy at the bottom of the hill? We have to do it a different way. We can't just plug in 1/2 mv squared because we don't know the v at the bottom. How are we going to do this? Well, here's our setup. We know the total energy at the top is 1779 joules, and then you slice down the hill. Wait a minute. Conservation of energy, right? When you add up all the energy, the total energy, it should be constant. So let's figure this out. He's going to go down the hill, and this is ice and snow, so we're going to say, let's say there's no friction. No friction, so no loss of energy as he goes down the hill. So maybe we can figure out like this. The total energy at the bottom. So we should be able, oh, this is easy. What's going to be the total energy of the kid at the bottom of the hill? And remember, the energy stays constant. Conservation energy. So total energy at the bottom of the hill, how much? Well, the energy at the top of the hill is 1779, and total energy is conserved, so it's constant. So then the bottom of the hill is going to be 1779, the same amount. So now we know at the bottom the energy is going to be the potential plus the kinetic. Well, first of all, what's the potential energy of the sled at the very bottom of the hill? I'll give you a hint. You got to think about the height. What's the potential energy at the bottom of the hill? Zero. Zero height. He's at the bottom. No height. All height's here. So zero potential. So now kinetic energy. Wow, this is pretty not too tough. We know the total energy and we know the potential is zero. So what's the kinetic energy have to be at the bottom of the hill? It's got to be 1779 because all the energy from the potential was converted into kinetic. All right, so I do want to note something to you. This is actually the maximum kinetic energy possible for this guy's sled trip. Okay, this is if there's no friction. The most kinetic energy you can ever have on this trip is 1779 because that's the energy he has at the top. The only thing that can happen now is as he goes down, there could be friction, and friction would take some of this energy away and turn it into heat. That's the only thing that can happen. So this is the maximum kinetic energy, and it happens to be at the lowest point. Let's kind of review this with our example from last week with the pendulum. So here's our pendulum simulator again, and I have it on pause. I'm going to take this mass, and the mass is 1 kilogram. This red mass, I'm going to lift it up, and I'm doing work. I'm doing force through a distance, and you can figure out, if I bring out the ruler, you can measure, you know, how high, how far did I lift it from here up to there. It looks like I did about 10, 20, 30, about 0.35 meters of height, and then the mass is 1, so 1 times 0.35 times h mgh, and you can figure out the potential energy. So you should be able to do that. Figure out the potential energy like we did last week. MGH, potential energy stored in the system. And you can look over here on our bar graph. I'm going to zoom in a little bit. All this blue here is potential energy. The pendulum has lots of potential energy, MGH. And that's the total energy, right? The total energy is potential plus kinetic. And right now, it's all potential. It's at the top and it's not moving. It's stopped at the top. And then I'm going to hit play. I'm going to hit slow motion right away. Play and let it fall. And as it falls, you can see what happens again to the energy. Okay, and the green is going to be the kinetic energy, and the total energy is both of them added together. So once again, we're at the top. Here we go at the top right here. It's the highest height, so it's all potential energy. And then I'll let it go down towards the bottom, and I'll pause it right at the bottom, right there. And you can see now over here at the bottom, it's all kinetic energy. The total energy is now all green. It's turned to kinetic energy. And then as the pendulum keeps going, it's going to go all the way up to the top again over here. I'm going to pause right there. And now it's all blue. The total energy is all potential energy. So just like we did in our example with the kid on the sled, the kid started up here. It was all potential. Then he slid down the hill, turned all into kinetic. So if you know the potential energy up here, you know the total energy. And then you know down at the bottom of the motion, that's where it's all kinetic. It's easy to figure out the kinetic energy at the bottom because it's the same as it was the potential energy at the top. So you should be able to calculate potential energy using MGH, and then you know the kinetic energy at the bottom is going to be equal to the same thing as the potential energy at the top, because it switched from potential to kinetic, and then it keeps doing that back and forth to go to normal speed. And it just does it back and forth, back and forth, back and forth, because we have no friction in here, so none of the energy is being lost or turned into heat. So now let's try to look at what you will be doing for your lab. Okay, so you're going to open up your Conservation of Energy lab. It'll have your name up here. Just looking at, students will examine how kinetic and potential energy interact with each other. So you'll see some more of those bar graphs and do a couple calculations. And mostly you're answering questions to show that you learned about potential and kinetic energy and conservation of energy over the past few weeks. So you see lots of green. You guys are going to be replacing all of the green. Okay, there's one more example there. All these green you fill in with your own answers. Okay, and then one part here, you have a problem to solve with GUESS givens. Okay, we'll get to that. Back at the top. First part, in here, in the space provided, define the following words. So kinetic energy, what's the definition of kinetic energy? Delete that and fill it in. And you'll notice here, I put word banks. So you have, in parentheses, you'll often have a word or two that you need to use to get the answer completely correct. So you have to use the word speed here somehow. Gravitational potential energy, delete these words, put in the definition. You have to use the word height somehow for gravitational potential energy. Then open the link here. You click on this and open it. It'll open up the interactive, and you could click on intro, and there is your skateboard park thing. Woo! Okay, so let's go back to our document. It says click intro, slow motion, set your mass to small, and click on grid. So let me go back to here. I like to drag this off so I can Alt tab. So I'm going to reset this. It says click on intro. I did that. Slow motion. So slow motion. Then mass to small. So mass to small. Ooh, look, guy. And then click on grid. Grid. Where's grid? Oh, grid. This is going to do a graph or something? Oh, look at this. We have the meters. 1, 2, 3, 4, 5, 6. We have meters now. So now we have our meters, and that means we can get our heights. And the mass is a small mass. Let's get some information on that. Start your skater at the top of the track. Explain what happens to the skater. Starting position, and then you can use the word meters. Result, what happens with the skater when you let go of him. You can use the word back. And then reasons why this happens, and use the word energy. We have our reasonings that have something to do with energy. So I'll go back to this. It says put him at the top. I'll let him go. We're in slow motion, and there he goes. And he's gonna go up, but he doesn't. Oh, didn't fly out the top. Interesting. Okay, and then look, he's back over here. Oh, and he didn't fly out the top. But oh, I do notice something. Look at that. He's back there. So, starting position, I've used something with meters. Oh, I see meters right here. Then result, what happened to his motion. It's something about describing the motion. And then why? Why does he doing what he's doing? What we're noticing has something to do with his energy and conservation of his energy. I bet there's no friction on this track, probably. All right, so you fill those in. And then click on bar graph and run them through the track again, and use this to help you talk about kinetic and potential energy. So bar graph is right here. And then, oh, there they are. They look familiar. There's potential and kinetic. Potential and kinetic. And the total. It's a tiny bit of total, but potential and kinetic right there. It looks, something's happening with them. Oh, I can describe those with some words. The greatest potential energy, bottom or top. The greatest kinetic energy, bottom or top. I'll let you figure those out. Then you scroll on down here. What's the relationship between potential and height? So you gotta use the word height, obviously, in your explanation, but what's the relationship between potential and height? So potential energy versus height relationship. And then go down here, click on the speed. Click on the speed? Click on the speed. What's that? Oh, right there. There's a speed meter, and we can see the speed now. Oh, wait, look at the speed. Look at the speed doing. It's going down here. And then it's going up and back down again. Speed's going up and down. Oh, So what's the relationship between speed and kinetic energy? Oh, speed and kinetic energy. Kinetic energy is right here, and speed right there. Compare them. Write an answer. Okay? All right. Now, we're investigating here, investigate the effect of starting height. So now we're going to put him on, drag him and drop him halfway up the track. So now you can drag him, woo, and put him halfway, like right here, and figure out what's going to happen. I'm going to pause it for now. I'm not going to let you see that. You can figure it out yourself. What happens halfway, and compare, and use some words to describe what happened there. Okay? Then you're going to pause your skater and make sure your grid is clicked. Drag each top end of your track to 6 meters. Drag each end to 6 meters. I think it's already there. Okay. And then assume the skater is 70. You got his mass. You got the height, 6 meters. And then you calculate. You're going to go through here and calculate the potential energy of the skater. You use what we used earlier in the video today to figure out the potential energy. Then what's the maximum kinetic energy? Oh, there's maximum kinetic energy. We did that earlier today in our example with the kid on the snow. So you can figure out the maximum kinetic energy. Make sure you use the word joules. All right. And then that's it. That's the first. Oh, there's one more set. There's just 1, 2, 3, 4, 5, 6 more questions right here. Build a track. What? Under the playground menu at the bottom of the page. Build a track. What the heck? Playground menu. Oh, right here. Ooh. Oh. Drag this and put it up here. And then, ooh, look, there's a loop. You can put it. Drag this in. Ooh, there are points. Hey, what if I grab another one? Ooh, and connect them. Look at that. Oh, I can make another one. Ooh, you can do all kinds of, whoa. And put the guy on the track. And, oh, cool. All right. So you're going to build a track with a loop. It says you need 3 of those pieces. Okay, I got 3 pieces, but somehow I got to make it into a loop. Set your friction to none. That's important. Friction to none. So friction to none. That's going to be very different to have no friction now compared to having friction. And then explain what happens to your skater when you start at the top of the track. So you can make a loop, put him at the top track, and then let him go and see what happens. And click on grid. Make sure you have the grid clicked on like that, so you can get some answers. What happens if you start the skater on the ramp below the highest height? What can you say about kinetic and potential energy? Predict what happens to the speed at the top of the loop, and then do it and see what happens. And then you fill these out. So there you go. This is going to be your last assignment for this semester. Good luck.